Did you report the Tuesday one?
Yeah, it's up in Canvas.
Okay, okay.
All right, everybody, I think it is showtime, 2:00. Welcome. Welcome to Thursday, everybody. Hello, hello. I hope that your week is going well and you're staying air conditioned as much as possible. It's been a little toasty out there, but I guess it's supposed to cool down. We'll see someday. I've got a couple of quick comments here before we dive too far into everything. I've passed back those exams for the most part. I'm not going to go over the exam in class because I did send out a solution set that I wrote up myself. And I also sent you guys an email yesterday with some of the highlights of maybe what some of the issues were on a few of the problems. It could be anything from just didn't quite understand what the question was asking to, just getting two different concepts intertwined somehow or anything else. But certainly, if you want to talk to me personally about your exam or your standing in the class or anything like that, I had a couple people do that earlier today, and I think that was a good thing to do. Feel free to stop by my office hours, either in person or in Zoom, and I can kind of walk you through what I see is how things are going and maybe give you some advice if you need any. Overall, though, usually when I teach this class, there's a dip with the second exam. It's because the material is so much more abstract. We hit you over the head with vector spaces, which is like this big abstract concept where you have to really communicate the ideas and explain them in abstract terms. And that's quite different than what we did at the beginning of the semester when we were really still doing calculus, So I think sometimes the second exam does surprise people a little bit. So I was actually quite happy to see that a number of people did improve between the first exam and the second exam, which was very good to see. So let's try to keep that upward trajectory going. I think I will do review sessions the rest of the way through. I think that was helpful for some folks. Just going to keep encouraging you to stay as engaged as you can with the material. And I'll do everything I can to do what I know to try to get you through this and hopefully get you to have a good feeling about the material. So, but yeah, if you have any personal concerns or questions about sort of where things are standing with you, do let me know. I will remind you that in terms of the grades for this class, I do have a slightly more generous grading scale than maybe is standard. So to get an A, you need about 87.5. A B would be 65, and a C would be 62.5. I sometimes fudge a little bit on the lower end of the C range if I need to. Remember that I do give myself 2 to 3% of latitude for qualitative things that are not going to have numerical scores with them. That would be coming to office hours. That would be being engaged in the class, attending the class, doing the group works, participating. Improvement would be another thing that would fall into that category. So anything like that, so that if somebody, is really on an upward trajectory by the end of the semester, and if you're close to one of these cutoffs, I can justify bumping a person up if that's the case. The other thing is that the grade that you currently have in Canvas is, of course, lower than what your actual grade is. And that's because I have not reweighted the grade yet. In my syllabus, I explained that whatever the best part of your grade is, out of all the things we do, the exams and the homework and everything else, will get extra weight, an extra 5% weight. And I'll take that weight off of whatever the lowest thing is of those different exams or the homework for your situation. So typically that will raise people up roughly 3 or 4% is what I notice. It depends a little bit on your exact scores. But you're not going to see that in Canvas right now because I can't do the reweighting while we still have another exam to take and a final and all of that. So, but just keep that in mind. I think it's better to just play it straight exactly as you see it in Canvas is where you stand, but just know that there will be a little bit of a bump at the end that you don't know about yet or that you can't see yet. But anyway, so there's a lot of folks doing a good job. if you're not feeling so great about things and you want to just come get my advice, I'd be happy to talk to you personally. The university changed the policy a few years ago. It used to be that if you wanted to drop a class, you had to do it within the first month of the semester, or else you just had to write it out and just take an F or whatever you were gonna do. They've changed the policy now that you can still drop a class, and I don't like it when people drop my class, by the way, I'm not encouraging that in general. But, you know, in case it's something that you were thinking about, you do have until November 14th to skip out of here with a W. You have to fill out a form. I would automatically approve that form. I've pretty much been told to always approve that form, so you do have a couple of weeks to mull it over. We have a third midterm and a final still ahead of us, but I'd be happy to talk to you about that issue as well. If you're thinking, if you think that's something you should consider doing. But anyway, I don't think that many people need to consider doing it, but it is an option, and I feel like I should let you know that. Okay, let's get back to where we're actually at now, kind of thinking ahead. There is a homework assignment due tomorrow. So far, no problems have made it onto my sideboard, but during the break today, if anybody wants to throw some problems over there, I did about 2 or 3 of them in the morning class. So you guys would be welcome to add some problems there as well. It's just problems about the kernel and the range of a linear transformation. So we've been spending quite a bit of time on that already. But if there's homework questions on that, that would be fine. So that's homework number 16. So that's due tomorrow. We're kind of back into our regular pattern, guys. Homework 17 is the next one, and that will be due on Tuesday. And that's based also on a little bit of the stuff with one-to-one and onto transformations, along with the new material that we're going to cover today, which is we're going to start chapter 7 today, which is a completely different topic. So there'll be a mix of topics there. So these are the next 2 homeworks immediately in front of us that you should be working on and asking questions if you have any. Okay, I think that's about all I have by way of announcements. Just kind of back into our normal routine. We are finally almost at the end of October. This month just goes forever. I feel like I've had 11 lectures this month or something. It's some ridiculous amount. When we get to November, things will chill out a little bit. We have a holiday in a couple of weeks for Veterans Day, and then we have an entire week off for Thanksgiving. So there will be some time to catch up on sleep and catch up on any of the material that maybe you want to go back and focus back on. There will be some more time to do that next month. I think this has been a kind of a grueling stretch, if I could put it that way. But we're doing great. We're doing real good. I've got a recap over here on my board. Let me just make sure that I'm getting all of this. Looks like everything's good. This is the same picture that I drew up here on Tuesday of how I like to visualize linear transformations. These are functions, right? These are functions from one vector space to another. And what we know about them is that they have to respect the operations of the vector space. So a linear transformation, guys, it has to respect addition and scalar multiplication. And as long as we have a linear transformation, yeah, we can talk about this thing called the kernel and the range, which I put in the blue and in the red writing here on the board. The kernel is a subspace of V, and that was all of the vectors that get transformed to 0. So if you're doing the homework for tomorrow night and you're trying to figure out the kernel of something, this is the place to start. T of V, set it equal to 0, and then try to solve from there the equation that comes up, okay? So that's the kernel of a transformation. On the other hand, the range, which is in the red writing, that's a subspace of the W, right? So that's over on the right-hand side of the diagram. And this one, I put it down here, is the span of the list of transformed basis vectors of V. So you take a basis for V, transform all of those basis vectors, make a list, and throw them into this span. And that gives you a subspace of W, okay? So both the kernel and the range are subspaces. That means that they both have bases. They both have a dimension, right? All the concepts from chapter 4 that we learned, we can apply them to the kernel or to the range, for sure. And one thing we noticed on Tuesday, we did a whole bunch of examples on Tuesday. I made a whole table. I think it had like 7 different examples. What we noticed on those examples, as we were writing down the kernels and ranges of all of those examples, is that the sizes or the dimensions of those subspaces seem to play in opposite directions, right? So they actually add up to some fixed number, which is whatever the dimension of V is, right? So you'll know that number, presumably you'll know what the dimension of V is ahead of time. And then from there, these other 2 numbers have to add up to that. And so, if the kernel is bigger, then the range will be smaller. If the kernel is smaller, the range will be bigger. In terms of this picture, what I'm saying is if the blue part is smaller, then the red part would have to be bigger to make up for that. And vice versa, if the blue part is much bigger, if the kernel is much bigger, then we would expect the red part to be much smaller. So they go in opposite directions in that sense. Okay, but these 2 subspaces are clearly very much related to each other, and the general rank nullity theorem is as good of a evidence of that as anything. Right. Okay. Stop me with questions, guys, if there's anything as I'm going along here. I'm just reviewing again what we did previously. So the kernel and the range, and then we made these definitions here that are basically just, you just have to memorize these. It's not any big deal, but these are very common for mathematicians to look at. The one-to-one idea, right? The one-to-one transformations, those are just situations where the kernel is actually 0. So the blue part is completely collapsed to just the 0 vector. That's a one-to-one transformation. And then the onto concept is where the range of C is all of W, meaning that this red part is filling up the entire big circle of W. And that is also a possibility that we could see sometimes. So a transformation might be one-to-one, it might be onto, or it could be both. In which case it's called an isomorphism. And we talked about this also on Tuesday. So isomorphisms really are very, very nice linear transformations where you not only respect the vector space operations, you also have, a very small kernel and a very big range. Yeah.
Are kernel subspaces?
Yes,
Yeah,
kernel,
okay.
the kernel is a subspace of V. We proved that on Tuesday. And the range is also a subspace of W because it's a span. So these are 2 subspaces.
Oh, yeah.
That's why we can talk about their dimensions right here. Yeah. I don't know how else to say it, guys. You just need to learn these bullet points, some of these facts here, get some flashcards going. Don't wait till 2 days before the midterm to decide you're going to memorize everything. I would start learning it now. Spend a little bit of time with it as much as you can to get this down. So the first one is that if V is bigger than W, right? If V is bigger than W, then there's no way that T could ever possibly be one-to-one. You don't even have to tell me what your formula is for T. Doesn't matter. It will not be one-to-one. It might be onto. That would require us to think about whether the range was equal to W or not, but it's for sure not one-to-one. Okay. Second bullet point is just turning everything around. If V is smaller than W, then there is no way that T could be onto. You can try to be the cleverest that you could making up a formula. It will never work. You cannot make an onto transformation in that case. And you have a maybe on the one-to-one for that scenario. And really the best scenario is when the 2 vector spaces have the same dimension. If V and W are both the same dimension, then there is a chance at least that you have an isomorphism. Right, there's a chance of it, but it says here both or neither. So it could end up failing both, but it can't be one without the other. In that case, it's both or neither. Okay, so that is just a quick summary of the high points of what we talked about last time. Are there any questions so far? So far, so good. Great. It's great to see all of you guys here, by the way. I love it. We're going to do a quick warm-up problem, and then I'm going to turn you guys loose on the group work. I just passed out a group work. Not everybody maybe got it, but I've got more copies up here for anybody who missed it. But before we do that, let's just do one quick warm-up problem first. just to play with these concepts. This one will be quick. This isn't gonna take very long. The warm-up goes something like this. Let's suppose that T is a linear transformation. It's gonna go from P6 of R to M2 of R. And let's suppose that this is linear with the dimension of the kernel of T equal to 3. So let's suppose that the kernel is 3-dimensional. And then the question we're gonna ask is, well, it's the one I've been playing with already on Tuesday. Is T 1-to-1 onto both or neither? Very common question. On my next midterm, third midterm, you're gonna see questions like this. I'll give you a transformation, ask you, is it 1-to-1 onto both or neither? Now, in this case, I didn't actually give you the formula for T. Instead, I gave you some sort of abstract information that we have to work with. So remember that on these 4-part multiple choice questions, we can always rule out 2 of the wrong answers immediately. Because these facts right here will allow me to say that T can't be one thing or can't be another thing, right? So we can like cross off, let's try to cross off some wrong answers first, and then kind of go at it from there. Can somebody remind me, what is the dimension of P6 of R?
7.
That would be 7, right? It's always n plus 1, so that would be 7. And then what about the dimension of M2 of R?
4.
That's 4, exactly. So the V and the W, right? This is the V, this is the W, right? And so in this case, the V is bigger than the W, right? The dimension of V is bigger than W. So what's it say here? It says T cannot be 1-to-1. I'm gonna cross off 1-to-1. And of course, if it's not 1-to-1, it's not gonna be both. So the only remaining question is that T might be onto. And the onto question involves this definition. T is onto if the range equals W. So we need to figure out something about the range of this transformation. Now, they didn't say anything about the range in this question. They instead talked to us about the kernel. So how are we going to bring the range into the picture if they only gave us the information regarding the kernel? Yes, Michelle.
Since we know the dimension of the kernel, we can do the general range of the
Yeah. Did everybody catch that? This is the big theorem that relates the kernel with the range, right? These dimensions. I love it. So we know the dimension of the kernel is 3, right? We know the dimension of V, we said that was 7. So we're just trying to fill in this little box here, figure out what the dimension of the range is. Okay, so I think we can probably handle that. Let's just write it down. The dimension of the range of T is equal to the dimension of V minus the dimension of the kernel of T. If I just sort of move the equation around like so. And now I'll just sub in my numbers. That would just be 7 minus 3. They gave us the dimension of the kernel as 3. So this just becomes 4. So the dimension of the range is 4. Based on that, would you tell me that this is onto or that it's not onto? It is onto. Why is it onto? Look at W, right? W is 4-dimensional. The range of T is 4-dimensional. They're the same size, right? And the range of T is a subspace of W. So because they're the same size, they have to be equal. So this is equal. Let's just add one more line here, guys. This is equal to dim of W. This is equal to the dimension of W. Okay, and so that means that means that the range of T does equal W. And so T is onto. The correct answer on this one would be that it is onto. Okay, make a little bit of sense? Okay, questions at all? If not, what I'd like to do, guys, is spend the next few minutes playing around with this group work number 10. And again, I know not everybody maybe has it quite yet. This group work has 2 problems on it. What I'd like you to do is grab 2 or 3 partners, and we've got whiteboards all over the room, and see if you can spend a few minutes working out these problems. Luis, I assume you'll be able to help me out. I'll come running around helping you guys out, but let's see if we can solve these 2 problems. Go ahead and have at it.
Yeah. It's literally gonna be my first time doing any of this, so I'm down. Let's do it. I've been like,
I know it's doing here
last Tuesday and this Tuesday. It's because I had a doctor's appointment. But I thought it was last Tuesday, but it was this Tuesday. So I missed both classes. I know, I'm bad, dude.
Give it up.
No, I'm good at. I've been on the sick one this semester.
Let's see, you need the handout? Yeah. There you go. Chris, do you need this handout?
Alright, so
Anybody else needs a handout?
so we're giving me
Sorry.
Yeah, like. Very plastic.
I mean, no. I meant like, yeah.
Gabriel, not quite. Read that really carefully on W.
There's.
Guys, I have a quick hint for you. Really quick, a quick hint on problem 1, the dimension of W is not 4. Read very carefully what W is. I'll come around and help you if you need it. It is not 4.
It means it in all.
I don't know what it's from.
This is symmetric matrix, it's all equals 0. You know what? Yeah, sorry, I didn't call you yesterday. I was having
So.
We have to stop for.
It's bigger than W. I erased your. There. Yes. W is only 3-dimensional. Yes, that is right. That is very good. Sorry. You can remove the 1 to 1. Yeah, take the span of each of those. So TM 100 and TM 0100. Yeah, that's it. Plug it in there. Yep, that's it. That's it. I'm going to say you're right, but let's say, I'm just gonna argue that. Let's say that you feel really sure. Okay, so even though the question is, but maybe it's on to, You might find this odd to believe, but I might be able to decide what I'm on to. By actually doing it. No, my LW is. If I figure out. Then I'll be able, without even touching the range, I can figure out. Using this example. I'm not saying you have to do that.
But it's not.
Number of people that want to have, decide how to figure out the kernel of this problem. And then figure this number out, and then through the staff or about figuring out. So that is something. So honestly, we have.
So the. We found out.
Love this. Yeah, this is gonna be.
Yeah.
So you're doing this, and you're rating these like 3, and what is the beat? And then you're discussing. By 2 symmetric matrix.
Basically, you got it. Okay, that's, yeah.
2 by 2 symmetric matrix. Here, right? And then number here. But then the thing is, this number has to match that. Because they're both symmetric. This is the B and the B, right? And then this one would be some other. I plus that out. How many vectors are there? So what's the dimension of W? So your dimension of W is your range. W is. So this is like 4, 3. Because of that, definitely not. Definitely not. So it has to either be onto or easy. To figure that out.
What does it mean?
Dimension of that and range of dimension. I do have one little goal. Which is.
Oh, yeah, you're right.
If this matrix was LD relative to X, it's like throwing it away from it. And if you were throwing it away, then you should say. Right, so it's actually not totally clear. To decide if this really was a basis, you would need to like lay these vectors.
So there should be.
Same thing.
It's fine.
I mean, it's just. I would just say. Show you the basis. Yeah. Do your EROs to it. But the point is, there's no free. Actually, yeah. So it is a basis. Some people are in my morning class, they were tracing. I got one other. Find out eventually with all of these equations. That A, B, C all have. But the. That would actually. I thought. Oh, yeah. Zero, zero, zero. And so I guess once the bus down that variable, so just wanted to find out. If the kernel has a one dimensional dimensions. So let's see, we're afraid of down the range. And if I.
Yeah, that was.
I can only get your box over there on that, we're on the left. I know that the kernel is one. And I know that B is.
Yeah, it's right.
And I can, by subtraction, figure out the range is three-dimensional without ever actually seeing the range. That's kind of a clever way to do it. Makes sense? Okay, it's okay. Anybody need a hand? Anybody need some help? Yes,
T1DC. We're pretty happy here. Yeah,
So is it like,
it's all.
Absolutely.
We said the rain or what would have been the other round.
Whatever the do the substitution.
It's not that bad. Yeah.
Learning pathway.
Yes.
Start over.
Well, it has to be. Well, then you just find like one by that's so much longer.
Well, learning both ways. Whatever.
Like this, like easy, right?
You really want to
So,
go. You guys. Having both ways.
So then, yeah. It's like and so. Say that yeah, because would be. Yeah. I see. So we have to see it in the West.
That's why it's a find out. It's a great decision.
You get that? Yeah. Cool, thank you. Like this.
I mean, if you want to be.
Wait,
I don't know how to study.
Oh, you did that.
That brain real quick. The thing is, when I do the things, I just do it. So.
Actually, it's shoved in. One plus, I know it's not. Oh, but it's got either way. If you went this route, yeah, but I never know this part of the range. It's still here.
Mary saw this now?
Yeah.
Trying to throw one of them away.
We didn't sit down. It's sleeping. I love it. Are you sir pretty? I think he like cuts this part off. No? Yeah.
How much?
Yes.
I did work. So my grade, we went from like 1% Oh, yeah, range was 3 to like 45. So basically, in this guy.
Anybody need a hand? Francis? Yeah, Leon?
Colonel.
All right, here's your formula. Right? And they're asking you about the kernel. So you're gonna set all those equal to zero. E is gonna be zero, so B is zero, A is zero, as soon as A is zero, C is zero. Okay, so they're all. Okay, so our general rank nullity here, which is like the most important thing ever, tells us that the dimension of the curve plus the dimension of the ring.
I can see the could.
This has to be, which right now is 30. So you just got 0. All right? So what is the dimension of the ring?
So because I want to throw it.
That has to be, or it has to be in some dimension. Or one box has to be. How do you find the range? Well, it's span of. That's all. These are polynomial sections. It should be something like, instead of 1, 0, 0, I would use x squared. Oh, yeah, you got some box here, right? Oh, yeah, exactly. So you already got that down. Let's see, x squared is whatever. Oh, yeah, so it's gonna be.
So it's just, that's, and then.
It does look correct.
It becomes the grade out of.
Yeah. They gave. So now, here's another question. Normally, I would look at these matrices. Normally, I would look at them and say, I don't know. Maybe they're LT. Maybe I can write this one. I don't know. Except, so you know that the range is three-dimensional. I've got personal times in front of me. That to me, amazing. It's one of the basics. You want me trying to throw something out. Some dimensions will go down to 2 or 1, and that's not gonna make this equation work. Okay, so this has to be 3.
But we put
So this has to be 6. This there, you are gonna love this there, and it makes so much simplification of your calculations.
Like, hell yeah.
So you take a basis for me. So I chose the nicest list that I know. Good job, good job. You guys know what you're doing. It's also 1 something.
Yeah, because considering it's very.
Yes, it's all
This Western. And it's been, it matches the dimension.
No, I think we need to add.
No.
Yeah, because,
This is going to be 1 to 1.
Check the work.
Yeah, what? Yeah. Oh, okay.
Remember the task. Remember when you're almost from 0 to 8.
Oh, you know what I know? Yes, I know what it is. There you go. It's also online. If you lose that, it's on the internet. Yeah.
Can I get a little help?
Yeah, I'll be right there. Okay, guys. Can I get everybody's attention? If you're done, feel free to take a little 10-minute break now. We'll kind of use this as a little bit of an early break today, and then we'll come back and start chapter 7 after a 10-minute break. But if you're still working, I'll come around and I'll tell you one more. Yes.
Make sure.
By the way.
Yeah, that's all I'm trying to figure out. If it's either one.
Fine.
If it's easy. Yeah, so. Yeah.
Colonel was. So if you're trying to figure out. Anybody else need a hand? Oh, Francis, you were asking for help. Were you asking me for help?
I'm trying to see if this is kind of, yeah, one-to-one or either.
Okay, I'll let Luis, help you out there.
Automatically. So what would this one be?
No, yeah.
Is less than,
Can't be on.
so, yeah, one to one or neither. So, it's actually one to one. I just got to figure that out. So it's like, what I was asking, but I just didn't. One to one.
Right.
Different favorite. So, exactly. Oh, this thing. What's it? Oh, so you need to, the kernel is 0 and it's 1. Yeah, you said it. You did that right here. So that was
You said you're.
I love how we look at our.
So one to one. Okay.
How are we? I just think of you.
Okay, that's one point. Yeah, I mean, you both, Bob, that's one.
I'm not trying not to walk through there. I was just trying to find out the problem.
But I'm just confused about.
Yeah, once we go back.
That's it.
That's.
You gotta check that.
That's a definition I can't remember. That one, I can remember that, but I don't know how to find a one-to-one or onto. I'm not gonna do that. That's what.
You're doing so well for yourself.
That's what I was trying to remember that. Okay. Thanks all this stuff during the test.
We're trying to look for the current one. So we did this.
I miss reading a lot of things.
Robin?
Yeah.
It's too much. We're talking too much.
That's what we got right there. Yeah. You got this.
Wait, I
So, yeah, we broke it up into like 2 days. How do we go that way? Combine it like this. So.
How do I figure it out? Oh, I mean, but you asked me. It can be really bad.
Yeah, guys, if you've got homework questions while we're taking a little short break right now, feel free to add them up on the sideboard over here.
Wait.
Yeah.
Yeah.
And then even if I'm sure, like.
I told them maybe see if it's, yeah, it's like.
Make it onto, give it a chance.
Like, I thought you.
Then you have to check it, yeah. The way it's set up now, if you go in the core, it has no chance. If the beams, then there's a chance it can be onto, but we don't even know that for sure.
Okay.
Anyway, we need to wrap it up though, in the next minute or so, sure.
Drawing your books, that's all that.
Oh, I accidentally took.
Is there anybody else who wasn't here on Tuesday? Just wondering, I've got this extra hand that I gave it to Rob. Everybody got my little hands, yeah, rib cheek. I think. I don't really.
Shut up.
Six and 12. That's why I didn't. That's why I didn't get on that question.
I could have gotten more. I didn't see. Wait, you for real? Show me the documents. Show me the documents. So never happy. He shows it. Photoshop.
Yeah.
But it's in a swamp. My comment is stuck to my head. Well, I was like this.
Yeah. How many girls you guys were?
Huh?
How many girls you guys were?
Every single one of them. We just kept talking, forgot it was here. So like, the lady, I'm like, you guys want to switch out your girl? You mean it's something slow?
Yeah, the marinated one always like bread on the road.
Yeah.
Yeah, I always order those last, like people go.
That makes sense.
Dry one.
We've already, we had our cook, CJ baby, we already, that code was all wrong. Fix it. It was wrong.
They have no cook?
That's what called me dumb, like, what about this here? Did you see? No errors in the actual page. I was ready to cancel like the real. Cause I loaded like this one, so we just want all one that's no people around. Is that one thing? It was really like in the front.
All right, everybody, I think most folks have made their way back over here. Thank you so much for your diligence on the group work. I think most groups managed to get through most of it. As always, one thing I always like to recommend is that you do go back to these group works. Especially because the solutions are in Canvas. I have a whole folder. It's just filled up with all the solutions to all the group works, and they're wide open. And so sometime, you know, in the weeks ahead, it's not a bad thing to go back to these group works. I will tell you that one of the challenges with this particular section is that we're not gonna take an exam on this for over a month. We're gonna have Thanksgiving break, or have a big long break and a lot of time off. So as fresh as it might feel right now in this moment, by the time we get to December, when we're getting ready to take a test, this is usually something people do have to come back and review. Because it just, there's a lot of time that goes by. But I hope that you're feeling pretty comfortable with linear transformations now. And kind of this idea of the kernel and the range. We are on the cusp, and I say that, on the cusp of going back to differential equations again. I just can't believe how fast the time goes by. But when we get to chapter 8, we are going to go back to differential equations. One of the many, many, many reasons that I love teaching this class so much is that the best is always yet to come. The finale of this class, the last month or so, we're going to go back to differential equations, and we're going to use all of this linear algebra to help us do so much more with it than we could have done even just a couple of months ago. So it's pretty cool where we're headed, but we do have one more thing that we need to talk about in the realm of linear algebra. I can't stand up here and tell you that I've taught you an authentic class on linear algebra if I don't talk about eigenvalues and eigenvectors. Some of you may have even heard of this already. It's a very, very important piece of linear algebra. And so we're going to spend one chapter on this, chapter 7. We're only going to do 3 sections of it, so it's only going to take us about a week to cover chapter 7 here. But let's talk a little bit. I'll give you an introduction to the theory of eigenvalues and eigenvectors in the second half of our class today. The first thing to know about this is that we're going to be working with matrices that are only going to have to be square size. So throughout chapter 7, The matrices that we are gonna look at will be n by n, okay? That's just the same as what we had to do when we were doing determinants. So you may remember back in chapter 3, every matrix in chapter 3 was also a square matrix. Well, that's gonna be true here as well. Now, let me write down, I'm just gonna jump right in, guys. I'm gonna give you the definition now of the eigenvalues and eigenvectors for a matrix. Okay, so here it is. The definition, if V is a vector and it's not the zero vector. Okay, so we're gonna throw away the zero vector from consideration here, but this is going to be a vector in Rn. And I kind of want you to be in your mind, I'll just draw it over here on the side. I want you to kind of visualize the vector as being presented vertically into a column. Now, I've already had somebody coming into my office hours recently, not so much about this, but something similar, who said, oh, on the back of the book, they write it as a row. And that is true. A lot of times, just to save space, trust me, my publisher was so much a stickler about this. We're not going to draw a lot of vertical columns in the book because it just uses up so much vertical space. So when you're looking in the book, you might see things written as a row, but I want you to visualize them in your mind right now as being columns, because that actually makes more sense. Okay, so we're going to view our vector like that. It's a non-zero vector in Rn, and so not only do we have this non-zero vector, we have a scalar. So this is called lambda. This is a Greek letter, and it's very standard in this series, so I don't want to deviate from it at all. Everybody uses the same notation. Lambda. It's a Greek letter that is just representing a number. It is a scalar. And then such that, and I'm now going to write down the most important equation in chapter 7. It's not taking me long to get there. This is the most important equation. You will all want to know this one well. A times V equals lambda times V. It's important enough to put it into a box. So A times V equals lambda times V. Okay, and I'll come back in a minute and talk more about what that really means. But A times V equals lambda times V. Then we call V an eigenvector. We call V an eigenvector of A. We call V an eigenvector of A with corresponding eigenvalue lambda. So the V is the eigenvector and the lambda is the eigenvalue. So we have these eigenvalues and eigenvectors, and then I can just, a lot of times we put the two things together. Together we have the eigenpair. So it's just another word, eigenpair, where you kind of group the lambda with the V together into a little parentheses around the two things together in that notation. Okay, so you cannot have eigenvectors without eigenvalues, and you cannot have eigenvalues without eigenvectors. They come as a package deal. So talking about an eigenpair actually makes a lot of sense. You would definitely think of that as being reasonable. And now you can kind of see, you can already see why I wanted you to visualize your vector as a column rather than a row, because I'm just going to scribble over here for a minute, guys. If A is n by n, and I want to multiply it by V, I can't multiply an n by n matrix by a row. I can only multiply it by a column, which would be an n by, sorry, this is a 1, an n by 1 column, right? This I can do. This dot is just matrix multiplication here. So I can do matrix multiplication with this V set up right here as a column, but I wouldn't write it as a row. Even if the back of the book puts answers as rows, I like to think of them as columns. It's a more appropriate way to think about that. Okay, so this is the idea, eigenvalues and eigenvectors. Actually, I should probably draw you an example or two. of this before we go any further. Let's just take an example to get the idea here. And I'm just gonna use a little 2x2 matrix, I think. That should do the purposes just fine. Let's make the matrix 6 and 4, and then 1 and 9. Okay, so there's a matrix, and I'm going to make a vector V. So V is going to be a vector, which is I'm going to use the vector 1, 1. And I'm going to take that vector and I'm just going to calculate, A times V and see what I get. All right, so let's take it here, A times V. So we write down the matrix A, 6 and 4, and then 1 and 9. I'm going to multiply that by the column of 1 and 1. And I'm just doing my matrix multiplication scheme that we've learned since way back at the beginning of the semester. So we go across the rows of the matrix on the left and down this column, and we do dot products. 6 plus 4, that's 10. And then 1 plus 9, that's 10 also. And what you'll notice is that the vector 1, 1 has turned into the vector 10, 10, which is literally just 10 times the vector that we started with. Right? That's actually what this box equation is suggesting. We took the vector 1, 1, and when we multiplied it by the matrix A, it got turned into 10 times itself, right? So V is an eigenvector, and I like to abbreviate eigenvector as just E vector to shorten the writing. And it is corresponding to the eigenvalue, which is going to be written as E value of lambda equals 10. Okay, so there you go. We have the eigenvalue, eigenvector pair. In fact, let's write that down as well. The eigenpair would be that we would put the 10 there along with the corresponding eigenvector. So there you go. They come as a package deal. We can't have the eigenvalue without the eigenvector. We can't have the eigenvector without the eigenvalue. Now, we can draw pictures of this, at least in the case of a 2x2 matrix. I can kind of give you a little visual to go right along with this as well. If I draw my little XY plane here, which I think of as R2, my original vector V is right here. So this is the vector 1, 1. I'm just kind of plotting roughly where that vector might be. And by the time I multiply V by A, what happens is it gets stretched. I'm going to move this R2 out of the way a little bit. This gets stretched by a factor of 10. And AV is the vector 10, 10. Right? And it's still pointing in the same direction. But what's happened here, guys, what's happened here is that the vector V has been stretched by a factor of 10. The lambda is actually telling us the stretch factor. So the vector 1, 1 has turned into the vector 10, 10 through the use of the matrix. By the way, this is not anything that bizarre. It's not like I've never talked about this before. Just last week, we talked about matrix transformations. If I give you a transformation from Rn to Rm, there will be an M by N matrix that goes with it. So right now, my 2x2 matrix would be this matrix. This matrix is a function. It drives this linear transformation so that I can plug something in like 1, 1 and get something out like 10, 10, right? So that's basically just what we're saying here is that we're viewing this matrix as a function that gets applied to a vector by just doing multiplication. That's exactly how that gets done. Okay, so it's not actually a new thing at all. But here we are focusing on square matrices only. And I'm focusing a little bit on what the impact is on the vectors. That's actually what I care about. So in fact, I actually want to just show you a couple more pictures. if I had a situation like this, let's just draw it on the side here. Let's suppose we have this vector v like that. If AV goes off like this, right? In this situation, notice that the vector v has been turned. It has been rotated so that it's not just a scalar multiple of the original vector. So this picture is showing a situation where v is not an eigenvector. It's not being stretched in the same direction by some factor. So that's not a situation that we're interested in right now. I keep talking about this thing as if it's always got to be a stretch factor. But of course, this lambda that we're talking about, this stretch factor of lambda, could be a number that's a fraction. It could be less than 1, and if that was the case, it would not be stretching the vector. It would actually be crunching it down. It would be smashing it into or shrinking it down into a shorter vector. So you could have v looking like that, and then AV could be right here. That would be fine. So in this picture, v is an eigenvector again. It's just now the vector has not really been stretched out to be longer. It's actually been crunched down to be shorter. But the key thing is it's pointing in the same direction. Yeah. Go ahead, Arlene. Question.
Could it be mirrored?
Exactly. Took the words right out of my mouth. The lambda value could also be a negative number. And if it was a negative number, what would happen is the AV could actually turn 180 degrees around the opposite direction. So if you take your vector and you multiply it by -10, right, it's going to still be along the same line, but it's going to face the opposite direction. Yeah, so that's also possible. Okay, so the main thing is the vector should have the same orientation. It should not be rotating left or right. It should just stay right along the same direction as the original vector v itself. Okay? So far, so good? Now, folks are gonna have questions for me pretty quickly, I imagine. You might be maybe you're out there with this question. You're probably like, who cares? What's the big deal about eigenvalues and eigenvectors? That's a great question. I can tell you right now that everybody should care about them. There are massive applications of this, which we're going to get into. But I want to address a different question first, which is just how in the world do you find these eigenvalue, eigenvector pairs? Here, I just sort of pulled 1, 1 out of the sky and it worked. I had plenty of time before class to prepare this lecture to find something that would work. But how do you, in general, find these things? So that is actually what I want to talk about first here in this next little whiteboard. So how can we find the eigenvalues / eigenvectors of a matrix A, which is an n by n matrix? So if I give you some n by n matrix, this would be, the next question that I would want to address. How can we find them for ourselves? Rather than just sort of guessing them or pulling them out of the sky, is there a method to obtain them for ourselves? And since this is such an important topic, everybody does need to be able to do this. Of course, these days there's online calculators you can plug a square matrix into, and within seconds you'll have the eigenvalues and eigenvectors, right? But we need to know how to do this conceptually for ourselves. There's something about pencil and paper that still makes sense when you're trying to theoretically and conceptually understand something. And so we're going to do it right here, okay? It just means that I have to give you mostly small matrices. You're usually going to be looking at 3 by 3s, maybe a 2 by 2 from time to time, or a 4 by 4 from time to time. But the sweet spot of the size that's pretty reasonable to do with a pencil is a 3 by 3 size. So let's take a look here. So actually, to find these eigenpairs, we usually start with the eigenvalues. So lambda is an eigenvalue of A if and only if. And now I'm going to give you hopefully a recipe for coming up with these lambda values. So we already, the first line I'm gonna write down is basically just the definition again. The definition is that there exists a vector v not equal to 0 in Rn with A times V equals lambda times V. So that's the starting point. So an eigenvalue has to have a corresponding eigenvector. They have to go hand in hand. And so that's just more or less the definition being recopied from the original definition. Now, what I'm gonna do, guys, is I'm gonna just take this equation. By the way, this is the most important equation in chapter 7. A times V equals lambda times V. And I'm going to subtract everything to the left side. And I'm going to make a mistake on purpose that I'm going to see if anybody can tell me what's wrong. First of all, I'm not going to write all those words again because it's just the same words. But I'm going to subtract everything to the left side. And I need somebody to tell me what is wrong with what I just did when I subtracted everything to the left side of the equation. It's leaving me with a 0 on the right side. Would this be legitimate? You know what's wrong with it?
You're taking a matrix and subtracting a number.
Absolutely. It makes no sense to do that. I cannot take a 3x3 matrix and subtract a single number from it. That's like apples and oranges. They're not compatible. We learned when you do addition and subtraction of matrices, they have to be the same size. Well, I have a fix for this. You remember our good friend, the identity matrix, which acts like a 1 when you multiply by it? I can slip that identity matrix right in there. And that is a harmless thing to do. Identity times V is still just V. So I haven't really done anything. Now I have a matrix minus a matrix. And just in case anybody's a little unclear, let me just put this over here. When I take lambda times the identity matrix, let's just make sure everybody knows what that is. That's just this matrix right here, guys, that has lambdas going all the way down the main diagonal and zeros everywhere else. So this is my lambda times I matrix. Okay. All right. Well, this is what we're saying. An eigenvalue should be a number such that you can find a vector such that A minus lambda I times that vector is equal to 0. Can somebody tell me what that tells me about this? So I'm going to put 0 not equal to V. Can somebody tell me what this equation right here tells me about V relative to the matrix in front of it? Am I asking my question correctly? Has anybody ever seen this in this class where we have a matrix times a vector, the other side of the equation is equal to 0, and we're trying to think about what the x is? What was that referring to? The null space of the matrix, isn't it? Yes, it is the null space of the matrix. Guys, this vector V lives in the null space of A minus lambda I. That's right. So we have, ooh, that's interesting. This null space has a non-zero vector in it. I want you to think about that for a second. Before we get into that, this null space, everybody remembers, I think, that this null space is a subspace. Remember, we studied null space, row space, and column space. They were all subspaces. So this null space is a subspace, and there is a name for it and a notation for it. And I'm going to add that to my notes right now. E sub lambda is the way I'm going to denote this. And this is equal to the eigenspace. The eigenspace of A corresponding to lambda. So it's a subspace. It's a subspace. So I know I sort of started off this little talk saying that I wanted to figure out how to find the eigenvalues. But I'm actually saying a little bit right now about the eigenvectors. These eigenvectors, they live in this subspace, which is this eigenspace that we're going to call it. Okay, so the E sub lambda. By the way, guys, I hope you all love null spaces. I know we've calculated a lot of them. You haven't seen anything yet. Chapter 7, there are gonna be null spaces running around in your dreams at night. I mean, they are everywhere, as you can see right here. Okay, so just get ready for that. It's coming up. Okay, I'm gonna take this another step further. Can somebody tell me if I have a null space of a matrix? Here's my matrix. I have a null space of a matrix that's not zero, because there's at least one vector in it. This eigenvector V is in it. If a matrix has a null space that's not zero, does that tell me anything about that matrix? I know it's super theoretical. It's conceptual. Chris, do you want to give it a shot? The matrix is not invertible. Wow, people are learning stuff in this class. I love it. Your invertible matrix theorem here, A, B, C, D, E, F, G, H, just last week we did it. We said that if A is invertible, its null space will be zero. Right? And right now I have a matrix whose null space is not zero. That means that this matrix, A minus lambda I, as Chris just said, it is not invertible. It is not invertible. That's exactly right. It is not invertible. Because the null space of an invertible matrix has to be zero. If you're solving this equation, when A is invertible, X will have to be zero. Right, okay. Well, now let's just remember something else about this invertibility of matrices. If a matrix is not invertible, what would you tell me about its determinant? It has to be zero, exactly. So the determinant of A minus lambda I is equal to zero. I'm gonna put this equation in a box as well, because you know what? That equation is the second most important equation in chapter 7, behind the one that we sort of started off with at the beginning. So this equation is so important that it has a name, and I'm sorry, I'm gonna squeeze this on the bottom of my board here. It is called the characteristic equation. So when we talk about solving the characteristic equation, we're talking about this determinant equation right here. And the goal of it is to solve for lambda. Remember, the eigenvalues are the numbers that will make this determinant equal to zero. So if anybody ever thought that this class went in a million different directions and was unconnected, it couldn't be further from the truth. On this board, we're talking now about eigenvalues and eigenvectors. I'm still seeing null spaces. I'm still seeing determinants. I'm still seeing the idea of vectors that have to solve equations. It's all still here, guys. It's all still here. Let's try an actual example now.
Okay.
Question first, please.
I was following along up until well, still afterwards, but the zero vector not equal to the.
Not equal to V.
Could you explain that part?
Well, my definition of an eigenvector, sure. But the definition of an eigenvector is it has to be a non-zero vector.
Okay.
So if I'm going to be looking for eigenvalues and eigenvectors, then I'm going to be looking for these lambda values for which there is a corresponding eigenvector. And the rule of our definition over there says it should not be zero.
Okay.
It's almost by definition more than anything else that's required. So I'm just taking this and I'm putting it right there. And I'm just saying, well, but wait a minute, the V is actually in the null space of this matrix based on this box right here. So this null space has something in it that's not zero.
Okay.
I don't even know what V is yet, but it's a non-zero vector that's in that null space. So we know that our null space is not zero, which means that we know that our matrix is not invertible. Yes, Seth. Why it's not invertible? Sure, it's because for an invertible matrix, if you have a system of equations like this, and if the coefficient matrix is invertible, you can essentially cancel it and conclude that the only solution to that system would have been x equals 0, right? But we're saying here that there is a V that's not 0 that is in that null space that solves that system. And that means that the matrix is not invertible. Great point. Yeah. So it's a little theoretical, guys, but the theory is actually going to kind of drift into the background pretty soon. We're going to get into the nuts and bolts of how you actually calculate this stuff. But again, I mean, I could have just walked in here. I could have just walked in here and said, here's the equation. Here's how you find the eigenvalues, right? And then figure out a null space and you're done. But you have to understand how this stuff ties together, right? That would be the much better way to appreciate the material. So let's do an actual example. Go back up here and see if we can find some eigenvalues and eigenvectors. Oh, and since the eigenvectors live in a subspace, I can ask you to give me a basis of them, right? Anytime you have a subspace, there's going to be a basis, there's going to be a dimension. Oh, that stuff is all going to be part of this, which is pretty sweet. You guys think I like this stuff? Just a little bit. Just a little bit. Okay. It never gets old. I keep thinking, one of these semesters, I'm going to come in here and it's going to be like, okay, I've done this 40 times. This is just, I always love it. Every time it's different. It's every time it's a little bit new. So, and I always discover something different each time I teach it too. So it's pretty fun. Let's try one together here, guys. I'll do an example. Okay. And let's just start easy. Let's just take a 2x2 matrix A. And this is going to be the matrix 1 and -3, and then 1 and 5. So just start with that. And what I would like to do is find bases. Bases is just the plural of basis, right? Find bases for the eigenspaces, the E spaces of A. Let's try to find bases for the eigenspaces of A. Okay. So again, the idea of this is going to be to try to find the eigenvalues first. And then in the process of that, the eigenvectors are just living in this eigenspace. That's how it's all going to tie together. So let's do it. Let's do the solution here. The first step is always to just sort of get going with the characteristic equation. So we're going to look at this determinant of A minus lambda I. And what is that matrix? Let's just be clear. Unfortunately, I just erased my thing. I meant to leave it up here. Lambda I is just this matrix with lambdas down the diagonal, right? I'm going to subtract this matrix from A. So here's A, and I'm going to be subtracting a matrix that's got 2 lambdas on the diagonal values. So the way that will look when I actually write it down is the diagonal entries of this matrix will have lambdas subtracted from them, like that. Okay, and this is a 2x2 determinant, and that's something we know how to solve. AD minus BC, right? So it goes way back to the beginning of the semester. 1 minus lambda times 5 minus lambda, and then plus 3. And I'm just going to go ahead and FOIL this out and simplify it. So if we multiplied this out, we would have a lambda squared. We would have a minus lambda and a minus 5 lambda, which is minus 6 lambda. And then we would have a 5 plus a 3, so that adds up to 8. So we get this quadratic formula. And what we have to do is set this equal to 0, right? That's the characteristic equation is setting equal to 0 here. Okay. Well, it's a quadratic equation. So we should never get too intimidated by that. Even if it does not factor nicely, it has to factor. And how can you always get the roots of any quadratic equation in any scenario? If I give you ax squared plus bx plus c, can you figure out the roots of it no matter what? We've got a quadratic formula, don't we? That's absolutely right. If necessary, we can fall back on that quadratic formula. By the way, guys, we're going to be using it a lot in the next few chapters. Yes. So we haven't used it much so far, but it is going to be important. So in this case, however, in this case, I have set up our first warm-up problem to be so easy that it factors really, really nicely. It's just gonna factor as lambda minus 4 times lambda minus 2. So you can just check that out, that we get lambda minus 4 times lambda minus 2. And that means that my lambda values are 4 and 2. There's gonna be 2 different eigenspaces, one for each of these lambdas. And what you might do if you're taking notes on this, guys, is make yourself a couple of columns here. And we'll just put these eigenvalues that we just found kind of as the headers of this column, of these columns. And we just have to go one at a time on these now and just work out the corresponding eigenvectors. Okay, so now I'm gonna work on the eigenspaces that go with these eigenvalues. And that means I'm gonna be doing these null spaces. Okay, so we're gonna be doing so many null spaces in this chapter. And what is the matrix that we are looking at? It's supposed to be A minus lambda I. Well, at this moment, my lambda is 4. So I'm taking A, which is here, and I'm going to subtract 4 from the main diagonal of A. So let's subtract 4 from the main diagonal of A. Is that a hand? You're good, okay. Subtract 4 from the main diagonal of A, and I get that right there. Now, as much as I think we would all love to believe that our algebra skills are flawless and that we would never, ever possibly mess this up down here, right? I do need to give you the troubleshooting manual on eigenvalues. The troubleshooting manual, because if you have these lambdas wrong somehow, and it does happen, if you factored it wrong or you wrote down a number wrong or whatever, and you come over here, how are you ever going to know that you were doing something wrong at any point along the way? Well, here is one test that you will know immediately. This matrix right here cannot be invertible, ever. It cannot be invertible because what was its determinant, right? The determinant of that matrix was 0. The matrix was not invertible. So if you come along here and you're looking at this matrix and you're saying, oh, that looks invertible to me, that probably means that your eigenvalue was incorrectly calculated. Just take a step. It happens to the best of us. I've done it too. If you make a little mistake, you just have to go back and check your eigenvalues again, okay? Anyway, I can see that these two rows are multiples of each other. If I was going to do these EROs, I would probably permute the two rows and then cross off one of them. I'm just going to cross one off right now. I'm going to get really sloppy and fast with my EROs now. So we just cross off that top row, and I'm going to circle a pivot right here. Okay? And we need to solve this null space. Let me get my variables x and y written down. Those are my variables for this null space, I guess. And then you can see that y is free. Call it t. And then if I just look at this equation, this is just x plus y. X plus y equals 0. So x would have to be negative t. All right, and so I can go right away to my basis. My basis for E sub lambda equals 4. I'm going to write it like that, guys. So I'll do my eigenspace notation. This is the eigenspace, right? E sub lambda. So, and what is it? Well, we make our little set here, and I'm going to bust out that t. And by the time I bust out that t, I've just got -1 and 1. If you wanted to make sure that that really did work, you could come back to the original matrix A and put -1, 1 there. And if you calculate this, if you do this calculation, let's just do it. If I do this matrix multiplication here, I'm going to get -1 plus -3, which is -4. And I'm going to get -1 plus 5, which is 4. So look at that. -1, 1 turned into -4, 4. The stretch factor is exactly 4, which is our lambda. It seems reasonable that this is a correct calculation. Okay, so there's your basis for the first eigenspace right here. Yeah? Slow me down if there's any question. So I've got my two eigenvalues. I just did the first eigenspace, but I also have to do the other one. Let's just do the other one really quickly. I have another null space to do. I have to start over. I basically have to start over here, guys, and do a whole new matrix. This time, I'm going to only subtract 2 from the main diagonal of A. So I go back to A, I subtract 2 from the main diagonal, and I get -1 and -3 on the first row, and I get 1 and 3 on the second row. And again, this matrix should be not invertible. And I can see that those 2 rows are for sure multiples of each other. I'm gonna wipe one of them off, which you can wipe off whichever one you want. I kind of like to just keep the one that has the pivot already as a 1. And from there, I just set up my free variables again. So I'll have y equals t, and then x equals -3t. Agreed? And then so I can go straight to my basis for the eigenspace corresponding to lambda equals 2. And that basis would be, after I bust out the t, I'm just gonna have -3 and 1. Okay? Remember, guys, that anytime you're finding bases for things, there's more than one right answer. So, you know, if the back of the book person, whoever wrote that, can't imagine who that would have been. Whoever wrote the back of the book, if they crossed off the other row or something, then they might have set up their free variables differently and have a scalar multiple of this basis vector as their basis vector. That would also be fine. That would also be fine. Any questions on this example? Arlene, yes.
So when we cross out, the -1 and -3,
Yeah.
when we solve for the values, we only do the ones we didn't cross out.
Yeah, I'm only
Okay.
looking at that. That's
Okay,
right.
yeah.
Yeah, exactly. Yeah.
Sure.
It's basically because the other row is just redundant. It's just duplicating what the first row told us anyway. So it's just a little bit redundant. Yes, go ahead, Yolanda.
So I just have a random question.
That's fine.
So the vector in our basis for the eigenspace,
Yes,
that would be our eigenvector, right?
that's right. So like if I took this vector -3, 1, and I so if I did A times B, right? And I work this out, I'm gonna get -6 and 2, I believe. And that's a scalar multiple of the original vector, and the scalar is exactly the eigenvalue. Right, you can see that. This vector is double this vector. Okay, so I've kind of given you already, I feel like I've almost told the whole story already of how to find the eigenvalues and eigenvectors. I do want to make a couple of observations and remarks here though, guys, and then maybe we'll do one 3x3 example. In this case of these little 2x2 null spaces, I don't know if you've kind of noticed that if this row is like, it's 1 and 1, and then the vector turned into -1 and 1. And here we had a 1 and a 3, and the eigenvector turned into -3 and 1. You can almost start to realize that it's kind of unnecessary to like set up the free variables every time and bust them out, because you can see what's going to happen, right? And let's write it down. Basically, in computing the null space of just a little, 2x2. Well, even just, sorry, it's a 2x2, but you've gotten rid of one of the rows. If you just have like these two numbers like this, right? We may take our vector to be negative of the second one and then the first one. Do you see that? Like the 1 and the 3, the eigenvector turned into -3 and 1. Okay, I'm just trying to make your life a little, this is just a technicality. It's just like a shortcut. Okay, so if you see the two numbers, right, here you have 1 and 1. So here I'm gonna write down -1 and 1. Here I have 1 and 3. I'm gonna write down -3 and 1. By the way, you could also, I'll add this here. You could have put the minus sign on the other slot. It actually doesn't matter. And that's also fine. But you can write down your eigenvector pretty much for free. I like to refer to this as the A-B trick. So you may hear me use that phrase occasionally when I'm writing down an eigenvector. I'm basically trying to say that once I have this matrix, I can go straight to here. And I can go straight to here. I don't need to waste my time setting up free variables and all that, at least for this 2x2 scenario. Okay? Just a technicality. If you don't like this remark, just ignore it. You can still do it, setting up the free variables, it's not a problem. The next thing I'm gonna write down is much more important. And this is the thing that is gonna help you make sure that your eigenvalues are correct. Because as I've already said, if your eigenvalues are incorrect, you're gonna have trouble when you get to the null spaces. You're trying to solve them out and you're not getting anything to work. If your matrix was invertible here, think about it with me for a second. If your matrix was invertible, you would have gotten pivots doing this. And you would have gotten no free variables. I've seen this on students' exams many times before, where this is what they write down for their eigenvector. Because they had no free variables, so they had everything being 0. And that is true based on solving this system. But we know, don't we? We know that our eigenvectors should not be just 0. Right? So you got to be a little careful. You don't want to find yourself in this pickle right here. Okay? So I'm going to give you a way that I hope will help you get these eigenvalues correct. I'm going to call this fun facts about the eigenvalues. So I'm not going to prove these right now. This would be a Math 307 thing. And I used to in the old days, I didn't ever even present this in class, but I just think it's good to have a way to at least check that your lambdas are correct. The first fun fact is that if you add up all of your lambdas, and I don't know how many lambdas you have, that would depend on the matrix. But if you add up all of the lambdas that you have, it should add up to the trace of the matrix. Do we remember the trace? It was a very briefly mentioned thing. The trace is just, I'll just put it here in the notes in case you don't remember it. There was one homework problem about it weeks ago. The trace is just the sum of the main diagonal entries. So it's kind of an important thing, but I haven't done a lot with it this semester, but it's just what you get when you add up the main diagonal. So if somebody hands me this matrix right here, I already know before I take a breath that my lambdas had better add up to 6. So if I've got 4 and 2, that's kind of reassuring. That adds up to 6, okay? If they don't add up right, then that probably means you better check your factoring, make sure you got your algebra right here, and make sure that you are working with the correct lambdas. Okay. And then I have a second little fun fact for you guys as well, which is that if you multiply these lambdas, if you take the product of the lambdas, it should turn into the determinant of the matrix. So this is a second fun fact that we want to keep in mind. So when you look at this matrix here and you take the determinant of it, 5 minus -3, which is 8, right? That means that when I multiply my lambdas together, it should come out to 8. And again, if it doesn't, then there might be something wrong. We don't usually use these fun facts to find the lambdas in the first place, but we use these fun facts to check them once we've kind of figured them out through this characteristic equation. So it's good to know this just for the purposes of checking. For checking. That seem okay to everybody? Questions there? So I'm not going to prove that as much as I'd like to. We're just going to take that as a freebie. Okay, I'm going to do one more example here. And then we'll wait till next week to get any further on this, but we're at least getting some good background information here. This one, I want to do a 3x3. So I'd like to find bases for the eigenspaces of, and let me make this matrix A right here. Let's take the matrix 3, 0, 0, 0, 2, -1, and 1, -1, 2. This is similar to the problem we just did, but it's a 3x3 this time. hopefully still manageable by hand. But let's give it a try. Okay, so I've got a model for my work on the board here in the middle. We're gonna follow the same process. Okay, there's gonna be a few little bumps in the road, as we'll see, but let's just start off. I'm gonna set up my determinant. I'm gonna subtract lambda off of the main diagonal of this matrix. So 3 minus lambda, 0 and 0. And then 0, 2 minus lambda and -1. And then 1 and -1 and 2. Oh, sorry, 2 minus lambda. There we go. Okay. Now, you guys probably remember that I was a pretty good salesman about the arrow method. So back in chapter 3, when we were doing 3 by 3 determinants, I sort of showed you this arrow method for calculating them. That arrow method is not going to serve us as well anymore. The reason is, if you just look at the first arrow right here, you're gonna have 3 minus lambda, 2 minus lambda, 2 minus lambda. If you multiply all that all the way out, you've already got a lambda cubed. A cubic equation. Notice on the 2 by 2, we only ended up with a quadratic equation, which was not so bad. We could factor that, or we could use the quadratic formula if we had to. But now we're getting into the realm of cubic equations, which we don't have nice formulas for the roots of, yeah? So the problem here is, I don't really want to get this thing expanded out into a cubic, right? Especially if I don't have a calculator. So there's actually a better way to do this determinant. Does anybody have a suggestion what might work a little nicer for us here? Joel? Cofactor expansion, I agree with that. And do you have a row or a column that looks pretty favorable to use?
Maybe the first row.
The first row is looking great, isn't it? I've got a couple of zeros in that row. I think that looks really good. I'm gonna expand on row 1. And I'm going to show you that by doing that, this turns out quite nice. When I do the first row, I take 3 minus lambda. By the way, if anybody's forgotten cofactor expansion by now, this weekend would be a wonderful time to brush up a little bit. So you take, that row and column, you cross it out, and then you do the determinant of the little 2 by 2 minor that is right next to it here. So I'm just going to recopy that. But then the beauty of going along row 1 is that then the rest of the row 1 has no other terms. So -0 and +0. Okay. Now, the thing is that I'm going to rewrite this as 3 minus lambda, and then I'm going to do this little 2 by 2 determinant here. Okay, so it'll be 2 minus lambda times 2 minus lambda, and then -1. And the nice thing about how this is looking is that it's actually already partially factored. This 3 minus lambda can kind of be kept out of the way if I just leave it in front. And then let's just work in the brackets now. Inside of these brackets, I can just go ahead and expand this out. I'll have what? Lambda squared minus 4 lambda plus 3. Yeah? And so it's factored already, at least mostly factored, and the part in the brackets is a quadratic that I can factor easily. It turns out that factors as lambda minus 3 times lambda minus 1. And we can set that easily equal to 0 now. That would have been a lot harder if I had just done a whole big cubic equation and tried to look for the roots of it. This time, this cofactor method kind of got this 3 minus lambda out of my way, out in front, and I focused more on the quadratic part of it that's with that minor. Okay, so here's the thing. What are my lambda values, guys?
-3, 3, and 1.
Let's be careful. So 3 minus lambda, if I set that equal to 0, it becomes lambda equals
-3.
3.
Oh, yeah.
3, right?
Uh-huh.
This one here, lambda minus 3, what does the lambda become?
Oh, yeah, 3.
3, right? And what about the last term? 1, right? My eigenvalues are 3, 3, and 1. We need to record those repeats. It's gonna be important. Next week, I'm gonna talk about this. When the eigenvalues are repeating, we need to write them down with those repeats. For example, if I want to check my fun facts, the trace of this matrix, guys, is 7. 3 plus 2 plus 2 is 7. That's the main diagonal added together. If I don't write down my repeats, I'm gonna be confused that my numbers aren't adding up to 7. So make sure that you keep those repeats in there. And then you can kind of go from there. I'm gonna just kind of sketch this because I'm a little bit short on time here. I've only got a couple minutes to sort of write down these two eigenspaces now. This part pretty much runs the same as before. When lambda is equal to 3, we have to do a null space of the matrix that we get when we subtract 3 off of the main diagonal of A. So I go back to the original matrix A, and I just subtract 3 off of the main diagonal. Again, this matrix cannot be invertible. I see a row of zeros there, so that's pretty convincing, right? And you know, you can do a couple of EROs on this. I think I'm gonna just spit out the basis for you here, just to save a little time. What you're going to end up getting here, when you do that, you'll have, you know, a free variable for z, so I'll put that as a 1. And then the y plus z adds up to 0, so this y variable has to be -1. And then x turns out to have to be 0. So there's your basis vector there. Okay. And then on the other one here, lambda equals 1. Let's make another null space real quick, and then we'll get the eigenvector pretty quickly. I'm going to subtract 1 from the main diagonal of A. That's my new 3 by 3 null space that I have to do. Now, can I point something out with this one? I can already see a couple nice pivots getting started here, but I also know that this matrix is not invertible, which means that I know that if I were to do the EROs, I would have to get a row of zeros out of this. So you know what I'm gonna do? Without even thinking about it, I'm gonna cross off the third row. Because I know that that has to cross off. Why? Because this matrix is not invertible. When you take a matrix that's not invertible and you do EROs on it, I guarantee you, you're gonna get a row of zeros every time. So you might as well just cross it off. That when I draw a line through it, I mean, I'm just zeroing it out. Okay. And now we can again go straight to our basis here. I'll write it down and then we'll call it good. The z variable will be free, so that will turn into a 1. Y minus z should be 0, so y has to be the same as z. And then look at the first row, guys. 2x equals 0. So x is 0. So there's your basis for that eigenspace. And that's the story on that. Okay. Is that good enough? Okay. I'm out of time, but there were some problems on the sideboard over here. None of these are very long to explain. I might make a video. It will be 5 minutes or less, just to explain. I may not solve them fully, but just to talk about a little bit about those problems. I'll send it to you, or you can come by my office hours. It won't be too bad, I promise. But don't forget, the homework is due tomorrow night. Thanks, guys.
Thank
Great
you.
seeing you. Have a great rest of your Thursday.
You too.